So just remember the game plan. We got to find the two constants c and n0 such that f of n is less than or equal to c times g of n for all n greater or equal to n0. And you'll find very quickly that if you talk about different asymptotic notations, most of them have the same game plan. So that's why I'm only focusing on big O at this time, but I'll be talking about some other ones in the future. So just the big thing I really want you to get a grasp on from our definition is we need to identify those two constants, c and n0. And then on top of that, we also have to talk about how they have to satisfy this inequality we talked about. We have to show that c times g of n always dominates f after this point of n0 and on n0. So you're going to find that I'm going to give you a lot of little techniques you can use to make n0 very easy to pick. But the thing is, it isn't just as simple as that. You actually have to reason it out. Like I said, it's nice to be able to just pick out the two constants and say, here they are, suckers, I win. You can't just simply just do that, right? You have to show me why they work. Because that's much more meaningful than just give me the two constants. You also show me how I can figure them out for myself too. It's the why. So that's why we try to formulate a game plan when we go and explore these things. So I thought it would be a good idea we'd try just using the definition of big O, and we're going to kind of run blind into this one, and we'll see what we get from doing this, okay? So let's do an example. Let's try proving. We're going to try proving that n squared plus 2n plus 3 is big O of n squared. So remember, when you see that fancy E symbol, I sometimes use that to say is, or is in. So normally I'd like to say what I'm going to do. So usually a good way to start a proof off is maybe tell your reader what the heck you're doing. It's usually a good idea. So we compute the constants. We need to compute the constants. So we're going to find these two constants. So remember, the game plan is simple. We find the two constants. I want to reason to you why you can use these two constants. And then I'm going to be able to say, hey, look, here's C, here's N0. I'm going to present them to you. And if these are okay, invoke the definition of big O and you're done. That's the strategy we're going to use. So I'm going to compute these two constants. I'm going to explain. I'm going to usually pick one of the two first. Sometimes it's useful to pick one over another first. Sometimes you can pick both at the same time. There's not one hard or fast rule for doing this. You'll just find very commonly that C is the easier one to pick out of the two. But it doesn't necessarily have to be like that. So we compute constants C, which is a positive real number, and N0, which is a positive integer, such that for all n greater or equal to N0, we write out the inequality, right? We write out what f of n is, so that's it's n squared plus 2n plus 3, which is less than or equal to c times n squared, right? This is me just laying out what we're going to do. Because if I just just run head first into this, and I just start picking stuff, I don't know what you're doing, right? So I like to make sure, you can argue that, Dan, you're kind of telling me how I should write out a proof for this. Now, there isn't just one way to do this. This is just a suggested way of going about this. There's several other ways. But most certainly, a good strategy when you write out a proof is tell the reader what you're doing. That's usually a good place to start. So then what I'm going to do is I'm going to try picking a constant. Now, like I said, I'm going to just go blind into this. I'm just going to try to guess some number for C, okay? So I'm not kidding. I'm just going to guess one. I'm not going to pick a very smart one. I'm just going to guess one. So if I look at the left-hand side, you see I have an n squared, a 2n, and a 3. Notice that I can't pick C to be 1. Because if I pick C to be 1, notice that there's still 2n plus 3 right here. There's this right here. That means the left-hand side will still be larger if I pick C to be equal to 1. So what I'm going to do is I'm going to try picking c to be 2, and then we'll see what we can get for n0 from here. So I'm just going to kind of go into this blind, and we'll see what happens. We're going to pick c is equal to 2. Then now I'm just going to find n0, right? Then we find n0. So that for all n greater or equal to n0, we have n squared plus 2n plus 3 is less than or equal to 2n squared. Now, when I look at this, the first thing I'm going to try doing is try to get rid of the n squareds, or at least whatever I could do with the n squareds. I'm going to try to eliminate this to make this simpler. Usually that's a good place to start. Usually I like to say what I'm doing. If not, you trust your reader to understand what you're writing. So if you don't trust your reader to understand the steps you're using, elaborate. Usually that's a good strategy when you're writing out a proof. So I'm going to rewriting the inequality. Rewriting the inequality by subtracting. I was about to write subtracting by subtracting n squared plus 2 from both sides of the inequality. Both sides of the inequality. We get the following. So I'm just going to subtract that off of both sides. This is because I want to make it simpler for me to make some judgment call on what n0 should be. So what I'm saying is that n squared plus 2n plus 3 is less than or equal to 2n squared is for, and keep in mind, I have not specified a domain. I'm just rewriting the inequality. You have to be very careful when you write these things out, because notice that I'm not specifying when this is true or if this is true or anything like that. I'm just saying I'm rewriting the inequality. So this is no different. I'm using this backwards, this back and forth arrow. This means if and only if, like I talked about earlier. So this double-sided arrow just means if and only if. It means that these are two equivalent statements. If and only if n squared minus 2n is greater or equal to 3. So I've subtracted n squared plus 2n from both sides. So notice that means that if you take n squared plus 2n, you subtract that from both sides, you'll have a 3 on one side, and then you'll have 1n squared left on this side, and then you'll still have the 2n on the other side. So now we have n squared minus 2n is greater or equal to 3. Now, you might say, Dan, it's obvious that n squared minus 2n is greater or equal to 3. That is a very impulsive thing to write right after this. Be like, Dan, that has to be obvious, right? Because that's a quadratic, that's a linear function, and that's a 3 over there. Well, certainly as n gets big enough, it'll be the case. Well, I don't want to quickly just say, obviously it's this, or clearly it's this. I want to give it the reason why that is the case. So I'm going to have to use a little bit more massaging to make this look a little bit more obvious to somebody that's looking at it. And I don't mean that as it's obvious as that's the reason. I'm trying to give a reason why this inequality over here has to be true for some value of n and on. So let's do that. And once we have that, we can get n0. But notice I'm just going like blind into this. You might ask, Dan, why did you pick that c? Well, like I said, I just wanted to make it kind of bigger that it wouldn't get consumed by the left-hand side. But the issue with that is that I have to be a bit more careful about n0 selection. I'm going to give you some tools for how to avoid this, so that it's easy as pie, not like the constant or something. I just literally mean like a very delicious pie, to come up with this result. So let's see what we could do about this. So next what I'm going to do is I'm going to factor the left-hand side of that inequality. Next, factoring the left-hand side so I'll abbreviate this as LHS very often of the inequality. Then that means that notice I had n squared minus 2n, right? So if I have n minus 2 and I multiply this by n, I get n squared minus 2n, right? That's the same thing as me writing n squared minus 2n. And the right-hand side was 3, right? Well, I wrote it like this to make it easier for you to see what n0 should be. Because at first you might say, okay, well, what value of n works? Well, if you look at this very carefully, we're making kind of two presumptions here. First, I would like to make them as simple as possible. Now, I'm arguing to you that you can get even easier than just this for the way you pick the constants. But here, if you look carefully at this, look at this, is notice that for n greater or equal to 3, the left-hand side is strictly positive, meaning it's a strictly positive number. It's strictly positive. Why is this? Because, well, first, n itself is always going to be a positive integer, right? But notice here that if I pick n is 3 or greater, notice that it's going to be 3 minus 2 is 1, 4 minus 2 would be 2, 5 minus 2 is 3, and so on. This always will increase in its value because n may get larger, right? But the thing is, I would need to... Now, here's the neat thing. If I even sure I have n is greater or equal to 3, I can guarantee this fact, right? So this is strictly positive because n minus 2 is greater or equal to 1, and the product of a positive integer, I'm just going to abbreviate that, positive integer, with another positive integer is positive, right? But it's even better than that. I just don't have to say positive. I can say this is greater than 0. But here's the catch. Here's the catch. So now I know it's greater or equal to 0, right? But I could do even better than that. Furthermore, if n is greater or equal to 3, meaning I give you a number that's 3 or greater, notice that this n times n minus 2, this part right here becomes greater or equal to 1. Notice the n minus 2 now becomes 1 or greater. That means that if I plug in n, in this case, notice that that has to be greater or equal to 3. Because if I use n as 3, that's it right here, right? It'd be 3 times 1. There's 3 right there. Notice that if I have 4, it'll be whatever 4 is, so the input itself, times whatever the input is, minus 2. But remember, now this is bigger than 1. So most certainly 4 times a number that's bigger than 1, which 4 is greater than 3, right? Will only make an even larger integer, right? So this we get our key ingredient here. So we're just going to pick, we can pick n0 to be 3. So everywhere on 3 and after, you can guarantee that that inequality is going to get satisfied. Now, I must stress, like I said, that n0 could be 4, it could be 5, it could be 6, it could be 7, it could be 10,000 if you want it to be. Mathematically speaking, the M word, the dreaded M word, you can pick any one of these, but 3 is the smallest one that makes it easier for me to justify to you. Therefore, so now I'm going to, like I said, I got the two constants. I've shown you how you could come up with them. Now I'm just going to present them to you. I'm just going to invoke the definition of big O. So now I have the two constants, and I've checked them for you. Therefore, so remember, this isn't just some magic here. This is actually a part of the argument. So I gave you the two constants. Now you got to use the definition of big O and to confirm it. Therefore, by selecting such C and N0 by the definition of big O, then we can have that n squared plus 2n plus 3 is big O of n squared. And we're done. Normally I mark the end of the proofs with this box here. So this is just an example of me just going head first into this. Now, are there any questions about this example? Or is this pretty clear? So do you see how I can just like go by magic, the two constants work? I tried to justify the selections to you, but I'm using an argument to do this. I'm not just simply just wiggling my fingers and say, okay, pick C as 2 and pick N0 to be 3. I actually am trying to show you where those come from. If I pick one of them, I show you how to get the other one. Because as long as they exist, right? It's not that there isn't some magic two constants that always work. There might actually be a whole set of two constants that actually work. There might be whole sets of pairs of them. Sometimes there might only be one pair. There might actually be like a magic two that only work. There may actually be none if it is the case that F is not big O of G. But yeah, so what I'm going to show you is there's actually a much easier way of going about this. So by the end of this session, you'll actually have a way of proving this without needing to pull out fancy tricks like this. And in fact, also, one other thing I want to point out to you is there's other ways you can derive these constants, like C and N0. You can use, for example, root solving techniques. So for example, you'll notice how I rewrote the inequality, right? Well, what if you treated this inequality like an equation and you try to solve for roots? Well, you would find, for example, that you might end up with the N0 that I have, but here's the catch. This is the big catch, is that you're all working on the presumption that whatever inequality you're playing around with will always be satisfied after that point. So you have to still have a reason for that. For example, you might say, oh, because the function is increasing, so on, so on, so on, so on. Use some calculus to justify this. If you define the complexity function by expanding its domain to, for example, to real numbers, or you define the, well, I technically speaking, you'd be okay still, but if you compute the, like, say the derivative and you show that one part of the inequality is always going to grow faster than the other, that's another way you could justify these things. But these are much more complex than just simply arguing things about products of numbers. Like, this is far more elementary. And very simple and easy things to justify are often your best friend when you want to convince somebody that doesn't understand what you're talking about. That's at least the way I like to view these things. You could use a sledgehammer if you want. I'm going to give you some simple ways to argue these things, but they do also exist. The other fault that you can run into with root solving approaches, which, like I said, you're more than welcome to use them, they exist, is that it also, like I said, there may exist multiple roots, and the question is, which one do you pick? Which ones do you pick? Works on the presumption that you know which one is the largest root you could pick. And you know that there's no other point afterwards, and you have to know about the shape of the functions. You have to know it always goes up, it doesn't come back down on one of the two. So, like I said, we want to keep it simple. But that's another way you could go about this. I'm not going to focus so much on that here. So, I'm going to show you a couple of crafty little ways you could approach these big O proofs, such that you don't have to pull up machinery like this, even. You can keep it even simpler. Now, with much more sophisticated functions, you may have to do more work than just even this. But most certainly, there exist other ways you can deal with things like polynomials that are in a much easier way. So, anyways, let me show you a quick little trick. And you're going to see that this trick is actually going to lead to a much more general rule we can actually come up with. And I'll include this proof. I'll give you a sketch of the proof in a moment. So I'm going to lovingly call this technique lookalike. So this trick I'm going to do is I'm going to call it a lookalike. So we're going to first try to exercise the idea of playing lookalike. You're going to see what I mean in a moment. Okay, so we're going to try playing this idea of what we're going to call lookalike. So we're going to call this playing lookalike. And this works pretty well for a lot of simpler functions. Like, for some reason I wrote lookable. That's kind of funky. Lookalike. And the reason why I say that is that I want to come up with a function that's easy enough for me to describe to you, but when I pick out the constants, I want to make it mimic the left-hand side. So I want to make the right-hand side look alike the left-hand side. So that if I could get that so that either they're equal or greater on the larger side, presumably the c times g of n side, then we're done. But if I pick it in the appropriate way, I'm going to try to make it look very similar to what's on the left-hand side. That's the game we're going to play. So you know how we had that example earlier where I had 6n cubed and I told you it was big O of n cubed? We're going to do an example like this. So we're going to prove that 6n squared is big O of n squared. So we're going to prove 6n squared is big O of n squared using this lookalike approach. So remember the strategy I'm going to give you. So just a little bit of side work here. You know that we're going to have those two constants such that 6n squared is less than or equal to c times n squared, right? What I would like to do is pick the constant so that this looks alike the left-hand side. Does anybody see an interesting way to make it so the right-hand side looks like the left-hand side over there? So I want to make it look as close as possible to what's on the left-hand side. And what I'm going to do is I'm going to just pretend that the terms I have on the right-hand side, even if they are more dominant, meaning they're like higher exponents in them, I'm going to try to make it so it looks like the left-hand side. Whether I'm going to take terms, I'm going to spread them out, or I'm going to just simply try to make it so they look identical. You're going to see this is actually going to generalize into a very nice technique for how we can play around with inequalities. So I'll give you a bit of a tip here. Notice that if I make this a 6, notice that 6n squared is less or equal to 6n squared. And notice that that means that this is actually an equality. It's not inequality, it's an equality. So let's use this idea. So as usual, I'm going to write out the game plan. We find constants. We find constants c and n0. Such that for all n greater or equal to n0, we have 6n squared is less or equal to c times n squared. Based on the strategy I had suggested to you, we're going to pick c is equal to 6, right? We're going to pick c is equal to 6. Then we're going to find n0, right? Then we need to find n0 so that 6n squared is less than or equal to 6n squared for all n greater or equal to n0. I know it looks very obvious, right? At this stage, we're basically done, right? But I have to tell you, just saying it's obvious isn't an argument, right? That is you deflecting the responsibility of explaining to somebody why something is actually true. One tip it's a little bit of a story, but it's not really a story per se. But very often, at least for the kind of research I do and the kind of work I've done over the years, the most common places that people make mistakes is when they say something's obvious or it's just cuz. Those are the most like if they say it's obvious or clearly it's the case, these are the most common places people make mistakes when they're reasoning. So just avoid using I usually, when I write out proofs, I try to avoid using those terms unless there's a common understanding among the audience what clearly and obviously mean. I try to avoid using those terms. They're usually reserved for the most blatantly clear things that you could think of, like 1 + 1 = 2, or that n is less or equal to n squared for all n is greater or equal to 1. So things like that at this level, those are what we would call obvious. So like this right here is pretty obvious, but because I want to give you a proof that gives you an explanation, I'm going to write out why that would be the case. So because I need to also tell you what n0 should be. So, well, for n greater or equal to 1, well, look, n is greater or equal to 1, so I'm specifying a domain for which the statement has to be true. Notice that this is an equality, right? It doesn't even need to be inequality, it's an equality. So I'm just going to say for all n greater or equal to 1, n greater or equal to 1, both sides of the inequality (6n squared is less or equal to 6n squared) are equal, right? So I'm just going to choose n0 to be 1. That's the smallest I can pick it. Don't pick n0 to be 0. n0 is equal to 1. Therefore, now remember, now I need to pick up that definition of big O and use it. Therefore, by the definition of big O, big O, 6n squared is big O of n squared. And we're done. Piece of cake, right? Do you see how this lookalike approach, I didn't go head first into this. I could have picked, for example, 7 as C. I could have picked 8 as C. I could have picked 9 as C. But notice that 6 here is just pretty easy for me to identify because I tried to mimic the left-hand side. So I'm going to show you another example of this lookalike kind of approach. You can apply this for other kinds of functions too. Just be careful, because when you jump from a polynomial to a logarithmic function, you have to be careful which one dominates the other when we talk about the sizes of the inputs of these functions. So let's do another example, just so you can get a flavor for what I'm talking about here. We'll get one with some multiple terms in there. And you will see that what we did at this first example here is actually a lot more work than we needed to do. And all it really is about comparing elements. That's really all I have to do. So let's do another example, everybody. So we're going to prove that n squared plus 12n is big O of n squared. Let's try doing this. Let's try this. Okay. So this looks kind of like my previous example, right? But notice now I have this plus 12n here. And the real question is what I do with that. Because one, I could just pick, say, for example, like C is 2, and I could get wherever, say, 12n gets beat by n squared at some point, right? I could do something like that in our first example, right? That's something actually we did before. That's fine. You can do that. But we're going to play this lookalike game again. So remember, I have n squared, and I have 12n. So I have two terms here on the left-hand side. Now, I have c times n squared at my disposal. So I get to pick what c is. So I have something that's going to look like n squared. And I have something that looks like an of n, but I'm only being able to operate with n squared terms. I would like to make it so that each of these looks like each one of these terms here. So notice that I have just one n squared there, and I have 12 n's right here. I'm going to try to match each one with an n squared. And like I said, n is less than or equal to n squared, right? It has to be that n itself has to be less than or equal to n squared for all n is equal to 1, right? So it doesn't matter that it's an n squared over there versus an n. I'm just going to try making them look like each other. And if I do this, it makes it easier for me to argue term-wise the truth of this inequality for some value of n and on. So this is going to be the game plan here. So let's do the proof. Again, so I'm going to say we need to find constants. So I first lay out the game plan. We need to find constants c, which is a positive real number, and n0, which is a positive integer, such that n squared plus 12n is less than or equal to c times n squared for all n greater or equal to n0. Now, if you look at my right-hand side here, up in my side work here, notice it's 1n squared, then I have a 12n squared. What should I pick for the constant c then? So I have 1n squared, I have a 12n squared. How many n squareds do I have? How many do I have? Do I have like 10 or 11 or 12? What do I got? Do I have 14? Do I have 15? Do I have 10,000? I have 13, right? I have 13 n squares sitting there on the right-hand side. So I'm going to pick c is equal to 13. Then I'm going to make an observation here, because I don't have a whole lot more I need to do. This is where I'm going to make my observation. Notice that for all n greater or equal to 1, so I'm making a statement about n greater or equal to 1. So for all n greater or equal to 1, the following is true. That n squared plus 12n is less than or equal to n squared plus 12n squared, which is equal to 13n squared, right? As the following is true. Now, I must stress that at this stage, I thought, oh, well, you could probably add a statement right here saying that we're going to find n0. But just for the sake of brevity with this example, I'm just going to cut it out. But I usually recommend you put the statement in there talking about how we're going to find n0 next. It makes the rest of argumentation a little more flow here. But I'm just going to keep it simple here. So now, you're going to see that this actually generalizes into a really nice argument. And I usually call this the bucketing approach. I don't know if there's any fancy name for it, but I'm going term by term, and I'm going to compare them just like I'm making lookalikes here. So notice that I have n squared, and I have an n squared, right? We know that n squared is less or equal to n squared. And this is true for all n greater or equal to 1, right? So we know that's true. This is, in fact, a true statement because they're equal to each other. But what about 12n? Actually, let me use a different color here. 12n versus 12n squared. Well, like I said, 12n is less than or equal to 12n squared, which if you really wanted to rewrite this, you could divide by 12 on both sides. You end up with n is less or equal to n squared. Divide by n, you'll end up with n is greater or equal to 1, right? Because we're presuming we're working with positive integers. So that means that this is true for all n greater or equal to 1. So notice that this is true for n is greater or equal to 1. This is true for n is greater or equal to 1. What if I add these two inequalities together? So I add all the stuff on the left side, and I add everything on the right side to the right side. So I have n squared plus 12n squared on the right-hand side, and I have n squared plus 12n on the left-hand side. Because this is less or equal, this is true for all n is greater or equal to 1. This is true for all n is greater or equal to 1. If I lump these into two buckets, most certainly it has to still be true, right? Why? Because this is less or equal to this is less or equal to this, right? And there's no way one is going to owe the other, right? These are both positive. In fact, they're both going to produce non-negative numbers, right? So you can't make an argument that one of these is going to sap away value from the other, okay? You can't do that. They're only going to get either the same value or they're going to get bigger. So you can use this kind of argument. So notice that if I add this and this together, you end up with what we have right here, right? There's your first one right here. The green stuff is this green right here. This stuff right here. So all it is just collecting things up into buckets, as we're going to see in a moment. So since this is true for all n is greater or equal to 1, then it means I could choose n0 to be choose n0 to be equal to 1. Therefore, by the definition of big O, then we could say that n squared plus 12n is big O of n squared. And we're done, everybody. We're done, everybody. Are there any questions about that example? I'm sort of leading us to where the kind of the underlying idea of this, what I'm calling the lookalike approach, leads us. We're going to see one more example like this so we get a real good mastery over how we are picking the constant c. Because the big thing that we're playing around with is c here, and notice that every example I've given you up to this point involves polynomials, but like I said, if these were logarithmic terms as well in here, you could also play this game too. Just you have to be careful when you're dealing with muddling around with different classes of functions. So I'm going to do one more example based on this idea, and it's going to generalize to the big idea I'm going to give you here shortly. So let's talk about this. So one more idea here. Well, one example. Okay. Okay, let's do another example here. So this is going to cement this idea a little bit more concretely. So we're going to prove that 4n to the power of 4. Now we're getting some larger powers here, but you're going to see it's not going to really matter much for us. At first, because a lot of the time when you start seeing things like with powers with 4 and 5 and 8 and 20, people look at it like, I don't know how to evaluate that very quickly, except with a calculator or something. Don't worry. You're going to see that our lookalike approach is completely impervious to this idea. It's not going to spook us or anything like that. So we're going to prove that this function here is big O of n to the 4. So just keep in mind what I said about lookalike. We're going to try to make the right-hand side of the inequality that we're going to derive look like what's on the left-hand side, which is sitting right here. So let's write out the game plan. So we find constants. C, which is a positive real number. That's what this means. And n0, which is a positive integer. Positive integer. Such that the following is true for all n is greater or equal to 1. Such that for every n greater or equal to n0, it has to be the following. It has to be that 4n to the power of 4 plus 3n to the power of 3, 2n to the power of 2 plus n, or 1 times n to the power of 1, is less or equal to c times n to the power of 4. Now, does anybody have any good suggestions for picking the constant c? So what's a good choice for c? There's a lot of different ones you can pick, but based on what the strategy I've been laying out, there's going to be one that's a really easy one to pick. And it will work in a way that's very similar to the other example. Well, let's look at it. I could distribute the c times n to the power 4. I can have 4 of those. I can have 3 of those, 2 of those, and then 1 of those. So I have 1 plus 2 plus 3, so that's 6, plus 4, that's 10. So I'm going to try picking c as 10, and let's see what happens with that. So I'm going to pick c as equal to 10, then we need to find n0 such that for all n greater or equal to n0, 4n to the power 4 plus 3n cubed plus 2n squared plus n is less than or equal to c times n to the power 4. So now we're going to make the same exact kind of reason, okay? So we're going to use the same kind of reasoning I did last time. Except now instead of having just 2 terms, I'm going to have 4 terms. I know the end cap of this makes it look like I have a 5th finger. I do have 5 fingers, but well, sorry. I guess I guess technically 5 digits, I guess would be the better way of saying this. I don't know. We're doing big O stuff, okay? We're having a good time. So anyways, well, observe that 4n to the power 4 plus 3n cubed plus 2n squared plus n is less than or equal to 4n to the power 4 plus 3n to the power 4 plus 2n to the power 4 plus n to the power 4, which this is all equal to 10n to the power 4, right? For all n greater or equal to 1 as for the following reason. We're going to use the exact same trick we just used, and I'm going to illustrate this using buckets, okay? So let's head over here. We're going to lay out the reasoning for this. So remember the rationales, we're going to go term by term through each one of these. We're going to go term by term. We're going to compare the 4n to the power 4 against the 4n to the power 4. We're going to compare the 3n cubed to the 3n to the power 4, and so on. We're going to compare each one of these. So, as 4n to the power 4 is less or equal to 4n to the power 4. Remember, we could justify this for all n is greater or equal to 1 because they're equal, right? It's going to end up that if you simplify this, you get 1 is less or equal to 1. For all n equal to 1. But here's the thing. Let's talk about this. Okay. Suppose that I have my 2 sides of my inequality. The one I wrote over there. We had each one of those. So imagine I have my left-hand side and my right-hand side. So every single time I introduce one term of some given power, like cubic or quartic or squared, etc., whatever it might be. When I have 4n to the power 4 compared against 4n to the power 4, I know that this inequality is true for all n is greater or equal to 1, right? So I could put 4n to the power 4s in the left-hand side, right? And for each one of those, I'm going to put 4 into this other bucket here. 1, 2, 3, 4. But I know whatever I put into this right bucket is going to always be either larger or equal to whatever quantity I put into the left bucket. So I can keep doing this, right? So notice that I have 4 here. So imagine that I'm, just for the sake of our discussion here, suppose I have 4 in here, and then I go to the next one where I have 3n cubed, right? So I have 3 of those I put in here. For each one of those, I put in a n to the power 4. So I put 3 of them into this bucket. And then I would put in 2 for each squared term, but then I would put 2 more n to the power 4s in here. and then I put in my 1n, I put an n to the power 4 in here, and you would compare the two, you weigh the two. Well, most certainly, and if I have this many in here, and there's either equal or larger quantities in the right bucket, you can argue very clearly when I add over all of them, it has to be the case when I put them all together, right? This is why I refer to this as kind of a bucketing approach with the way I argue this. It's like lumping sums in buckets, then I add over them as I add over the inequalities. So I sum over the inequalities to make this reasoning work. So that inequality works over there because this is true. 3n cubed is less than or equal to 3n to the power 4 for all n greater or equal to 1. 2n squared is less than or equal to 2n to the power 4 for all n greater or equal to 1. That r is looking a little sad. Let me fix that. And of course, I have n is less than or equal to n to the power 4 for all n greater or equal to 1. Notice that all of these statements are true for all n is greater or equal to 1, right? That means that the overall inequality has to be true for all n is greater or equal to 1, because notice that when I add this to this to this to this, I add all four of these together, I end up with what I have over there on the board. And that gives us what we need to demonstrate the claim. So remember, the idea is that I'm adding everything from the left side, like these are all going in the left bucket. Then I have everything on the right-hand side. All of these are larger or equal to whatever's on their left-hand side, meaning that whatever's on the left-hand side has to be either smaller or equal to what's in the right bucket, okay? So that's what we're doing here. And that's really what's happening. That's actually everything we've done up to this point, believe it or not. Therefore, by choosing n0 is equal to 1, we found C and n0 and by the definition of big O, big O, 4n to the power 4 plus 3n cubed plus 2n squared plus n is in fact big O of n to the power 4. So that's the lookalike approach in a nutshell. That's at least what I call it. I call it the lookalike approach because you're trying to make the right-hand side look alike the left-hand side, but you want to always do it such that everything on the right is going to be at least whatever's on the left-hand side. So that's the strategy of the lookalike approach.